So today we're going to look at the principle of mathematical induction here. So the principle of mathematical induction. Okay, so now the principle of mathematical induction, or rather mathematical induction, involves 4 steps of proving a given mathematical statement to show that it holds under mathematical induction, the same thing here. So we're going to say the process of proving by mathematical induction can be summarized into 4 ways. So here, the process of proving by induction can be summarized into 4 ways, or in 4 ways rather. Like this, yeah. So now, the first thing that we have to do here is when you're given an expression that you have to prove by induction, so you need first to prove that the given statement is true when n is equals to 1 there. So step number 1, we just have to prove that the given statement is true for n equals to 1. So here we're going to say step number 1 here. We need to prove that, or we need to show that the statement is true for n equal to 1. So here we say the statement is true for n equal to 1. So what this simply means is that if you're given an expression there, you get the expression on the left hand side and the expression on the right hand side. Then when you substitute where there's n, you substitute with the 1 there, your left hand side should be equal to your right hand side, this side. So if this holds, then we can simply say step number 1 is true there. So then after this, we go to step number 2. So we call step number 2 the inductive hypothesis. Here we assume that n is equal to an arbitrary element k. So for that statement there, it's just making an assumption there. So step number 2, we call it the inductive hypothesis. So here let's say inductive hypothesis. Okay, so under the inductive hypothesis here, we make an assumption where we say we assume that the statement is true. The statement or the given mathematical expression that you have. So in this case, I'll just be using a statement there. So we assume that the statement is true for n equal to k here. So here, this is where we get the s subscript kth term there. So we'll discuss this further when we start looking at examples. So after step number 2 here, we go to step number 4, or step number 3 rather. So here let's say step number 3. So now on step number 3, we just need to show that the next step of the inductive hypothesis is true. So meaning that here we just need to show that we continue with the assumption that we have on step number 2 here, where we made an assumption there that the statement is true for n equals to k. So if we move a step further from k here, we're going to the n equals to k plus 1 term. So meaning that here we need now to show that. So here we just say we show that, or rather we need to also show that the statement is true for n equals to k plus 1. So we moved a step further from the kth term, so we've added another term there. So it simply shows that if we add another term, is that statement still going to be true there? So here, what we simply do here on step number 3 here is we show this expression here where we say the sk plus 1th term should be equal to, this is the n equals to k, so this is the sk term that we have there. So, this is the k term that we have there. So meaning that if we add a new term to this term that we have already there, like this, so we're going to call the new term as the a subscript k plus 1 like this here. So meaning that on step number 3 here, we just need to show that the sk plus 1 term is going to be equal to sk plus ak plus 1 here. So understand this further when we start looking at examples there. So then step number 4 is just basically if all the 3 steps that we have on top here hold, then we can just make a conclusion from there that a given statement is true when n is equals to, or a given statement is true for all positive integers n there. So here we say on step number 4 here, so now suppose all the 3 suppose all the 3 steps above are true, then we can make a conclusion, or we make a conclusion that the statement is true so that the statement is true under mathematical induction. Okay, so now that we've done this, let's look at examples where we can prove all the steps that we have here. So let me just erase this here so that we can look at 1 or 2 examples there. Okay, so the first example that we have here, so let me just write example there. So the example that we have here is proof by induction. So saying proof by induction that the sum of the first n odd numbers n here, odd numbers, is n squared, like this here. So we're taught to say that is, so given the terms that make up this question that we have there, so we have 1 plus 3 plus 7, so 1 plus 3 plus 5 plus 7 plus plus there, open brackets, we have 2 n minus 1 being equal to n squared there, then we have for all n greater than or equal to 1, so meaning that n has to be a positive integer then. Okay, so now we're taught to say we need to prove by induction that the sum of the first n odd terms is n squared. So that is, we have these terms here that are being added, then we have another expression that we have here being equated to this n squared there. So now let's write solution here. So we start with step number 1. So for this example, I'll be writing, say, step number 1 there. Then the next examples will just go ahead and start solving here. So step number 1 here, we need to show that the statement is true for n equals to 1 here. So here we say we need to show that the statement is true for n equal to 1 there. So now what we're simply going to do here is we're going to get this expression that we have here of the last term of the terms that we have on the left hand side. We equate it to the right hand side, this side here. So what we're simply going to do there is we're going to get our 2n minus 1, we equate it to n squared like this here. So now, since we've said that we need to show that the statement is true for n equals to 1 here, so our goal here is we need to have the left hand side be equal to the right hand side like this here. So where there's n here, we're going to substitute with a 1, and where there's n this side, we'll also substitute with a 1 there. So that's basically just going to be 2 multiplied by 1 minus 1 being equal to 1 to the power 2 like this here. So 2 multiplied by 1 is just 2 there, minus 1 equal to 1 squared, just 1 this side. So let me scroll down a bit. Okay, so now here, you notice that 2 minus 1 here is simply going to give us a 1 there, which will be equal to 1 this side. So here we've shown to say that the left hand side is equal to the right hand side. So we can just say therefore true for n equal to 1. Okay, so now that we've shown that the statement is true for n equals to 1, then we go ahead and go to step number 2, which is the inductive hypothesis. So here, let me scroll down a bit again there. So let's say step number 2 here. So step number 2, we call it the inductive hypothesis. Okay, so on the inductive hypothesis here, we make an assumption now. We assume that, so here we assume that the statement is true. Okay, let me just do this a bit. Okay, so we assume that the statement is true for n equals to k. So as I said earlier on, so we're going to say the right hand side of this expression here, we're going to call it the s subscript k like this here. Okay, so now here, what we're simply just going to do here is where this n in the whole expression, both on the right hand side and on the left hand side, we're going to put k. So meaning that here, what we're simply going to do is we're going to get a 1 plus 3 plus 5 plus 7 plus all the way up to, so this is simply going to be 2k minus 1 being equal to sorry about that. So being equal to k squared like this. So on the inductive hypothesis, or rather on the second step, the only thing that we do here is to substitute where there's n, we substitute with k. So then we go to step number 3, where we need to show that the inductive hypothesis is also true if we add a new